Locked inside the tiniest of atoms is this absolutely immense power, enough to light up entire cities. For decades, we've been on this quest to figure out how to unlock it safely. So today, we're going inside the machine that tames the atom and turns it into electricity. It all kicks off with this number, 200 mega electron volts. So what is that? Well, it's the absolutely colossal amount of energy released when you split a single uranium atom. And to put that into perspective for you, the energy from just one tiny uranium pellet is the same as a ton of coal or almost 150 gallons of oil. It's just wild. So that's the multi-million-dollar question, right? How do you take that microscopic, incredibly powerful release of energy and control it so precisely that it can power your home? Well, that journey from a single atom to your light switch is honestly one of the greatest engineering feats of our time. Okay, so before we can build a machine to handle all that power, we gotta go back to basics. We need to understand nature's most powerful secret, the chain reaction. This is the heart of it all, nuclear fission. It's a pretty amazing process. It happens when the nucleus of a really heavy atom like uranium gets unstable and literally rips itself apart into smaller pieces. And that huge burst of energy, that's the atomic glue, the binding force that was holding the whole thing together. So the key is making this happen over and over again. It all starts with one single neutron. Think of it like an atomic cue ball that slams into a uranium nucleus. Boom! That nucleus splits, releasing energy and, this is the crucial part, 2 or 3 more neutrons. Those new neutrons fly out, hit other uranium atoms, and make them split, and on it goes. That's the chain reaction. It's like a cascade of atomic dominoes that creates a continuous, massive source of heat. Right. So a chain reaction that just goes, that's a bomb. And obviously we don't want that. So to generate power, we need a machine specifically designed for one thing, to control this process with absolute precision. So let's take a look inside the anatomy of a reactor. And this is it. This is a pressurized water reactor, or a PWR for short. I know it looks complex, but it's really just a super sophisticated system to start, sustain, and control that chain reaction we were just talking about. This design is the real workhorse of the global nuclear industry, generating about 85% of the world's nuclear electricity. The whole process begins with the fuel. These are tiny ceramic pellets of uranium oxide. And this is where you really see the incredible energy density of nuclear power. Get this, a single one of these little pellets, about the size of a gummy bear, contains the same amount of energy as a ton of coal. A reactor core is just packed with millions of these, all stacked inside long metal tubes called fuel rods. Now, for a really fascinating bit of physics. The neutrons that get released during fission are moving incredibly fast, way too fast to be easily caught by other uranium atoms, so you have to slow them down. In a PWR, the water all around the fuel rods acts as what's called a moderator. It's like a crowded room for the neutrons. As they bounce off the water molecules, they lose energy and slow down to the perfect speed to trigger the next split. But, okay, how do you control all of this? How do you keep it from getting out of hand? That's the job of the control rods. These are rods made of materials, like boron, that just love to absorb neutrons. By lowering them into the core, they soak up the extra neutrons and slow the chain reaction down. You raise them, it speeds up. They are literally the reactor's accelerator and its brakes, giving operators total control over the power output. And to contain all of this, the entire reactor core is housed inside this massive steel pressure vessel. I mean, we are talking about walls that are nearly a foot thick, weighing as much as a jumbo jet. And this is just the first of many, many layers of containment designed for extreme safety. Okay, so we've managed to generate a massive, controlled amount of heat inside that pressure vessel. Now what? The next big challenge is to get that heat out and turn it into electricity. This is the journey from the core all the way to your home. This is done using water in what's called the primary loop. This water gets pumped right through the reactor core, where it's heated by the fuel rods to an incredible 325 degrees Celsius. Now that's way, way over the boiling point, right? The only reason it stays liquid is because of the insane pressure in there, about 150 times higher than the air pressure around you right now. That super hot, pressurized water then flows into a steam generator. And this is a really, really important safety feature. The water from the reactor core, which is radioactive, flows through thousands of tiny tubes. The heat passes through the tube walls to boil water in a totally separate circuit called the secondary loop. The key thing is, the two bodies of water never actually touch. And from here on out, believe it or not, it works pretty much just like an old-school power plant. That clean, non-radioactive steam from the secondary loop expands, rushes down these giant pipes, and spins the blades of a massive turbine. The turbine spins a generator, and that's it. We've just turned the heat from splitting atoms into electricity. In the end, it's a very, very sophisticated way to boil water. Now, while the PWR is the most common design out there, it's definitely not the only game in town. Engineers have come up with a whole family of reactors, and each one has a different way of tackling the same fundamental challenge. For instance, take a look at the one on the right. That's a boiling water reactor, or BWR. It's got a simpler design. Instead of that second loop, it just boils the water directly in the reactor core. That steam then goes straight to the turbine. It's more direct, for sure, but it also means the turbine itself becomes part of the main reactor circuit. And this really shows you the kind of engineering trade-offs you have to make. The PWR's two-loop design is great for safety, but it has to operate under that extremely high pressure. The BWR is simpler and cheaper, but you have a potential radiation risk when you do maintenance on the turbines. And then you have other designs, like high-temperature gas-cooled reactors, that use helium gas to get even higher efficiency. But the story of the reactor doesn't stop here, not even close. All around the world, researchers are already engineering the next generation, designs that could totally change how we think about nuclear power. One of the most exciting developments is the Small Modular Reactor, or SMR. Instead of these giant, custom-built plants, the idea here is to mass-produce smaller reactor parts in a factory and then just assemble them where you need them. This could make nuclear power way cheaper, faster to build, and accessible to a lot more places. And their potential is, honestly, revolutionary. I mean, think about reactors small enough to power a remote research station in the Arctic, or to provide clean drinking water for a city in a drought, or to create the carbon-free hydrogen we need for the future. That's the promise of this new, flexible approach. And if you look even further down the road, you get to Generation 4. I mean, these are some really radical, bleeding-edge designs. You have molten salt reactors that could use liquid fuel and have incredible safety features. You've got fast reactors that could actually run on nuclear waste and breed more fuel than they use. These concepts are all about making nuclear even safer, more sustainable, and more efficient. Which brings us right back to the big picture, doesn't it? From harnessing the power of a single atom, to engineering these massive machines to control it, to dreaming up the next generation of reactors, the whole journey is driven by one of the biggest challenges we all face. The technology is incredibly complex, but the question it asks us is actually pretty simple, and it's one we all have to think about for our energy future.